Okay, so last time we discussed, we finished chapter 14. Now we are in chapter 15. This actually is the last chapter which I have to teach. If I have time, and I hope I will have time, then I will also teach parts of chapter 16, which is not part of the curriculum, but which is important for engineer students. Many of the results maybe from chapter 16 you have already used in other classes. So if I have time, I will at least try to teach some parts of chapter 16. It depends, because actually we still have a lot of time, 3 or 4 weeks, and we are rather quick. So, in chapter 15, what we want to do now is we want to extend the notation of integrals to functions of 2 variables. Now, for this, maybe just very quick review of the definition of the integral which we have seen last semester. So, what we our original motivation for defining an integral last semester was we looked at the function of one variable, non-negative, and now the classical problem is, okay, so you have a region here given by what is below the function above the x-axis between a and b, and what you want to do is you want to, the original problem reads you want to compute the area, but actually what you want to do is not compute the area, you want to define the area. Now, the approach we used last semester is, okay, we first divided the interval AB into subintervals, all of them of equal length. So we defined this delta x, which was b minus a over n, and then we defined the sequence of points xi, which was okay, starting from a plus and then I times delta x, where I is from 0 up to n. For n we get b, and then we were choosing a sample point in the ith subinterval. So what we do is, okay, so we have here a subdivision. So this a is x0, this would be here x1, this is x2, x3, x4, and b will be x5. And in every subinterval, what we do is we pick a point, sample point, and then we approximate the area which you see here by the sum of the area of the rectangles, whereas height you take the function evaluated as a sample point. So you have here f of xi star and then times delta x, and if this limit here exists, okay, then we are going to say that, okay, this area has meaning here. The area of the region has meaning, and we assign to this area, to the area of the region, this number here. Okay, of course, it's not enough that this limit exists. Okay, the limit should also be independent of the sequence of sample points you choose. But actually, last semester we haven't spent a lot of time discussing under which conditions does this limit exist. I just told you that if f is continuous, then it can be proved that this limit exists and is independent of the choice of the sample points. It gives you one number, and this number you take as the definition of this area here. Now, because apart from this from the area problem, we also saw a couple of other problems where the same limit appears. We decided to give this limit a name, and this was how we motivated last semester the definite integral. So the definite integral is defined by this limit. So for a function where this limit here exists and is independent of the choice of the sample points, you have this kind of notation here of the definite integral. And in case where f is larger or equal than 0, which corresponds to this situation here, the integral can be interpreted as a certain area. But if f does not satisfy this property, you do not have this interpretation, or I should say you have still the interpretation, but as a net area where you have to count parts where the function is above the x-axis as positive and otherwise negative. But you still have other problems, because for some functions might be so complicated that you're not even able to plot the graph, and then the meaning of this symbol here will become different, and it's not necessarily an area. We saw also last semester in the assignments examples for such functions. If you take the function which is like 1 at all the irrational numbers, 0 at all the irrational numbers, you can still ask whether this symbol makes sense or not. Okay, so this was last semester. Now, what we want to do is we want to consider the same problem. So the problem of finding now not the area but the volume of a function of two variables. So now we have given a function of two variables, which we also assume to be larger or equal than 0. So if you plot this, and we assume the function is given on a rectangle, which is AB in x direction and CD in y direction. Now, so you have in the xy plane you have this rectangle, and sitting above you have the graph of this function. And what we are interested in is the volume of the solid, which is below f and above this rectangle, and bounded here by this by the cylinder, by the cube given here from this rectangle. Now, okay, so what we can do here, of course, is we take the same approach. Maybe the best thing is here just to look at the picture, then things are pretty obvious. This rectangle, and you see the surface or the graph of this function sitting above this rectangle. Now, what we do is this is in complete analog to this situation here. So you see this here. What we do is we first divide the rectangle into smaller rectangles. We make a subdivision in x direction and in y direction. So we define here now the delta x, which is b minus a over n, and delta y, which is d minus c over, let's say, m. And then again, we define these sample points here. So we define here we get the sequence xi, which is delta x, a plus delta x I, and here we get the sequence yj, which is c plus j times delta y. The I goes from 0 to m to n, and the j goes from 0 to m. So we get rectangle, make everything consistent. Let's say we exclude this here, but this doesn't really matter. Like here, also here, it doesn't really matter whether you include this point or not. So in x direction, we choose here the i's rectangle, just the boundary points xi minus 1 xi, and in y direction, we choose the j's. Okay, so this is what you see here. So the rectangle Rij, here you see one of the rectangles Rij depicted. Now what we do is, okay, we pick a sample point inside this rectangle here, so call this sample point x. Now we have two coordinates, so xij bar, yij bar inside this star inside this rectangle. And what we do is we evaluate the function f at this sample point. This will give you what you see here, a certain height, and then of course if you look at a part at a solid which is bounded by this rectangle Rij and the surface, then this is not necessarily one of those rectangles you see here, but we can use a cube with the height f of xi, f of the evaluated at the sample point and the area of the rectangle in order to approximate our volume. Okay, so if we look at the ij's part of the volume, so we look at what is lying above the rectangle Rij and below the function, then this can be approximated by, okay, so you have here f evaluated at the sample point, and then you multiply with delta x, delta y. Okay, so this gives you one part here, one of those solids you see here, and now an approximation for the volume we wanna compute is given as follows. So I goes from 1 to n, j goes from 1 to m vij, which then is the sum I from 1 to n, sum j from 1 to m, and then f evaluated delta x, delta y. So you see that it should hold that v is given by, okay, now you just let the subdivision tend to infinity, the same thing as we have done for a function of one variable. So n and m both go to infinity, and you consider this here, the sum I from 1 to n, the sum j from 1 to m, f of x ij, y of ij star delta x, delta y. And this should give you the volume. Now, the reason why I say this should give you the volume is because you have to notice that the volume, we have defined the volume already for quite a lot of solids. Last semester, we used the method of cross sections and so on in order to compute the volume of certain solids. Now, this gives you a different method here to compute the same volume, okay? And actually, what you have to, strictly speaking, what you have to do here is you have to prove that this kind of limit will really tend to the volume for those surfaces where we have already defined a volume. But of course, this here is like this could be here a more general situation in the sense that it might be that you can that you encounter now solids which we could not handle with the method from last semester, but which we can handle now. Okay, so I think this idea is not very complicated to understand. This is just the same approach as we have seen for a function of one variable. Now, just everything in 2 dimensions. And again, we see that this kind of limit here, given a function, okay, on a rectangle, you can define these limits. This kind of limits here will play an important role. We will see that this limit not only shows up in this problem here, finding the volume of the solid below a function and above the x-axis, but also in other problems. In completely analog to the situation of last semester, we will give this limit an own name, and this is the so-called double integral. So we will use this symbol here. Maybe I should stress already at this point, not 2 integrals, right? These are not 2 integrals. Okay, this is one symbol here. Okay, this symbol is for this limit here. Okay, the reason why we use here 2 integral signs is because we see here 2 sums. Okay, but this doesn't necessarily mean that that you can compute something like this by doing 2 integrations. Okay, so this is the definition of the double integral. So more or less, if the function is if the function is non-negative, you can interpret this, the value here, which you get as a volume of the solid, which lies below F and above the region R, so the rectangle R, and also this is quite clear what this is supposed to mean. So what you do is just as in the as last semester, you divide the interval AB into subintervals, the interval CD, so you get them rectangles, and you approximate the volume by boxes, and you sum over the volume of the boxes instead of computing in order to approximate the volume you want to approximate, and that's the way we define the double integral. So let f be a function on a rectangle then the double integral, I just repeat this once more. So it's the limit n m tends to infinity sum now. Of course, there are several problems actually connected to such a definition. The first problem which we obviously have is, I haven't precisely explained what this limit is supposed to mean. Okay, but this is not a big problem because this is not you take first the limit with m and then you take the limit with n. It's not that simple because this is a little bit similar to if you have a function of two variables and you take a limit for a function of two variables. So what you require is okay, that for every epsilon, the distance between this this value here, which you claim to be this limit, and this double sequence here must be smaller than epsilon. So there must exist a large n such that the distance is smaller than epsilon, if n and m both are above this number n. So the definition for this limit is similar to the definition of limits we have already seen. Now this is the first simple remark, but the second not so trivial remark is, so the first question we encounter is obviously, okay, under which conditions does this limit here exist? So for which functions do we have here a limit? And more or less, the limit must be independent of the choice here of the sample points. Okay, so as last semester, this question I'm not going to discuss. If you are interested in such questions, you can, because the course is now almost over, so I can make some advertisement for our other courses. So if you're interested in questions like this, which are helpful in order to get much deeper into the theory of differentiation and integration, you can consider taking higher calculus of our department. Now, I just tell you that the obvious fact which you might guess is that if the function f is continuous, now it's a function of two variables. Okay, if the function f is continuous, then it can be proved that this limit here always exists and is independent of the choice of the sample points. So for a continuous function, this definition here makes sense. Okay, and most of the time we will see continuous function, not always. So this is a sufficient condition. Continuous will imply that this symbol here exists, but not necessarily. But it's not necessary. It's not if and only if. Okay. So even if the function is not continuous, this will still exist. But the function f should not behave too bad, in some sense. Okay. So if the function f behaves too badly, so if you change it just in one point, okay, there should be no difference here to the volume. Okay. So even if this function is not continuous in one point, it shouldn't make any difference. But this function should still behave nicely, that things are under control and this limit exists here. So this is an important remark, but we will drop more or less all these kind of details because we don't want to spend too much time discussing such kind of tedious details, but which are important in order to go much deeper into the theory. Now, another remark is this sum, because for a function of one variable, this sum was called Riemann sum. So here we have a similar name. So this is called double Riemann sum. Is Riemann spelled with one hand? Okay, so this is called here a double Riemann sum, and in case where f is non-negative, we saw already there is a nice interpretation of this limit if it exists. Namely, it gives you the volume of a solid. Now, of course, the next problem we have, the first problem is existence, but this we drop the details. Okay, we're not talking about too much about existence of this symbol here. For us, it's more important to figure out how to compute it, because this limit can be quite complicated. Okay, as you can imagine, even if I give you a simple function, you write down this limit, this double sum, you try to find the limit, it's a complicated problem. So the first question is, how to compute this symbol, and this will turn out to be not so complicated. The reason why this will be for most of the functions, this will turn out to be quite easy. The reason why this will turn out to be easy is because we can relate this problem to what we have learned, to theorems we have learned already last semester. Now, you should compare this with last semester, because last semester we also our first problem when we defined the integral was how to compute it, and now of course we know all how to compute a definite integral, but the theorem which was behind was the fundamental theorem of calculus, which was you can say one of the most important results we have learned last semester. So this problem didn't turn out to be that easy, and here we will essentially we will relate the problem to a problem to what we have done last semester now, out of battery. So okay, but before we go into discussing how to compute a double integral, of course one method we always have if we encounter a complicated integral and we are not sure how to evaluate this is we can use the computer. We can choose an n, we can choose an m, we can choose a sequence of sample points, and we evaluate the double Riemann sum instead of computing the integral, and we take this as an approximation for the value of the double integral. This is a method we can always use. Now, here, if you do such numerical computations, you still have freedom of choosing the sample points here, and we have here something similar to. Of course, for instance, you can choose as sample points always because you have rectangles now, and one possible choice would be you choose always the upper right corner, which would correspond to you choose this here to be equal to xi and this equal to yj. But another choice which gives you the so-called midpoint rule is you just choose the midpoints of every of those rectangles. So what you choose is xij is equal to xi minus 1 plus xi half, and so this we sometimes call xi bar, and yij bar is yj minus 1 plus yj half. Okay, then you get an approximation of the double integral which is roughly sum I from 1 to n, sum j from 1 to n, m, sorry. And then you have f of xi j bar, yi j bar, and then delta x, delta y. So this is the so-called midpoint rule. It's similar to what we have seen last semester. So this is one way of approximating a double integral. Now you find an example in our textbook. It's maybe interesting to look. Okay, so I just choose the same example as in our textbook. So x minus 3y square dA, and r is equal to xy. Okay, so this is the rectangle we are looking at. Now, depending on the number of sub-rectangles you use, for the subdivision of R, you get an approximation. Now here I use the whole, so I do not divide it. Here I always choose the same number along the R direction, along the x direction and the y direction. So here I use 2, and then I use 16, and then I use 64, and then 256, and then 1024. So what do I get? Minus 11.5. From here we see already this is not a volume. Minus 11.9687 minus 11.9922 minus 11.9980 and minus 11.9995. You see, you are able to find a better and better approximation by using the midpoint rule for this integral here. And you see, you easily end up with the guess that this integral should be equal to minus 12. You also see something, that the convergence actually is not that good. Okay, so you see that the speed of convergence is not that fast, because here you should have, like, you can be almost certain that this here and this here is correct, if you, because 12 is the same as 11.99999 and so on. So you can assume that those numbers here are all correct, but this one not. But you use already here quite a lot of subrectangles, so you have to do, because this will give you a double Riemann sum. You have to evaluate it, so you have to do already quite a lot of computations. And if you have a method which does not converge too quickly, it's always not so good to use it, because as you do more and more computations, there will be also an error coming from the computations, and you might not get a good enough result. Actually, just using this kind of double Riemann sums in order to approximate integrals in general doesn't give you very good approximations of an integral, and there's still a need to find a method to compute double integrals. Of course, in some situations, you can easily compute the double integral just by interpreting it as a volume. Like you see, if I give you, for instance, this example, so for this, we do not need any results which tell us how to compute double integrals in a more easier way, because you see that you just interpret this as a volume, because this is larger or equal than 0, so you can do this. So what we have is, okay, so z is equal to the square root of 4 minus y square. So what we have is z square plus y square is equal to 4, and z is larger or equal than 0. Okay, so this is just okay, and you integrate z from minus 2 to 2, and x from 0 to 3. Okay, and this is just the upper part of the cylinder. Okay, so for this you don't have to use any theory in order to compute this. Okay, so what we have is the height of this cylinder is 3, and you have a circle. This is a circular cylinder, so the circle has base radius r is equal to 2. So what you have is 4 times pi, and then half, which is 6 pi. So you see that in some cases and this is always the first thing you should try. Okay, the first thing you should try is you should figure out whether the integral can be easily interpreted as a volume of a certain solid, and whether you can compute the volume differently. Okay, this is always the first step. But we will see also later on. This example will not be very complicated. Also, with the general result, we will obtain in roughly 10 minutes. Okay, before we go on and really discuss how to compute double integrals, let's get some properties. Okay, so you have the usual properties. You have the double integral over some rectangle of a sum of two functions is equal to the sum of the double integrals. You have the property that the same for the difference. You have the property that if you have f of xy, of course, g of xy. You have that if you have a double integral where you have here a constant, then you can take out the constant. And you have also properties which are sometimes very useful is if you have a function which is always larger or equal than the other one, then on R, of course, then the double integral over the function f is also larger or equal than the double integral over the function g. Okay, so the usual properties prove everything easy just using limits. These are just the corresponding results for limits. Okay, and we know that the limit of a sum is the sum of the limits, and the limit of a function times c is c times the limit of the function, and so on. Okay, so now as I already mentioned, but the main problem for us is to understand how to compute the double integral. For this, we define first the so-called iterated integral. Okay, so assume we have a function f of xy, continuous function. On a rectangle AB CD. Let's because this is just technical, so let's say okay, this is included. Now what we can do is okay, we define a function which we call a of x, where we compute the integral from, because this function is continuous, so it will be continuous in this coordinate. If you fix x, it will be continuous as a function of y. So the integral which we defined last semester will exist. And then you can once more now, because this is a function of x, and this function can be proved to be continuous. If f is a continuous function, then it can be proved that this is also a continuous function. It's something you could guess, but still makes necessary a proof. So you can again compute the integral of this a of x now from x from a to b, And what you get is, okay, so we compute the integral from a to b, a of x dx. This can be done because a of x is continuous. And this will be called the iterated integral. So we first integrate from c to d f of x y with respect to y, and then the remaining the function we obtain as a function of x we integrate with respect to x. So this is called iterated integral. And similar in the other direction. Okay, so similar, we could first go with respect to x, and then we get a function of y, and then we compute the integral with respect to y. So similar, the integral from c to d, the integral from a to b, f of x, y, and then dx, dy. Okay, and in the sequel I will drop here the brackets. Okay, whenever we have an iterated integral, okay, we always will first compute the inner integral. So we always work from inside out. Okay, so I will, with this convention that whenever you see an iterated integral, we always work from inside out, then I can drop the brackets. And you see that what you see here, okay, it looks a little bit similar to the double integral. Now, maybe let's look at an example. For instance, the integral from 0 to 1, the integral from 0 to 1, and then let's say x squared y to the cube dy dx. Okay, so first we have to compute the inner integral. For the inner integral with respect to y, x is a constant, so we take out x squared. It's just a constant, and here we can use the fundamental theorem. And now this is the integral from 0 to 1. Okay, and then what do you have? 1 over 4, and then you have your x squared dx, and again we can use the fundamental theorem of calculus, and what we can get is 1 over 12. Now, how about the other direction? Okay, so how about the other direction? No, the same integral, but the role of x and y interchanged. Okay, if you do this, then you have the integral from 0 to 1. Now this is with respect to x, so you take out y to the cube, and then you go the integral from 0 to 1 x squared dx dy. Okay, so here you can use the fundamental theorem, so what you get is 1 over 3, and then you have the integral from 0 to 1 over y over cube dy. And now you use once more the fundamental theorem of calculus, and you get the same answer for this example. I should mention it's not always the case. Okay, if you interchange the integrals, okay, it's not always the same that you. It's not always the case that you get the same here. You can, for instance, try to plug. Try to plug the following function into Maple: x minus y. This function is slightly more complicated to integrate, okay? But Maple, no problem for Maple, because if you do this by hand, it's a little bit complicated. Okay, so you have here for the inner integral, you do it with respect to y, okay? But x is a constant, but it's a rational function, so we can integrate it. But maybe it is not sure whether you can integrate the resulting the result you get if you compute the inner integral. But if you use Maple, okay, so this is Maple. You get minus 1/2, and if you interchange (1/2), not the same. So it's not always that. Here we have been lucky. Okay. Here you saw. Okay. If you compute first, so the inner integral with respect to x, and then the inner integral with respect to y, and then the outer integral with respect to x, you get 1/12, and the same if you do it the other way around. Okay, so here for this situation we are quite lucky. Here for this situation we are not that lucky. Okay, because we get another value. I mean, it depends whether you consider this situation as unfortunate. Now, what we want to understand is, okay, under which conditions do we get the same? Okay, so under which conditions is the order of integration irrelevant for the result? Okay, and there is an important result of Fubini which tells you that you are lucky in almost all the situations. Namely, whenever f is a continuous function, okay, then it doesn't matter, okay, whether you compute this iterated integral or this one, you will always get the same result. So for a continuous function, so we see also where the problem here is, because this function not continuous at 0, okay, because not defined. But still, the integral exists here. Okay, so whenever you have a continuous function, you can interchange, and you have an iterated integral, you can change, you can flip the order of integration, and you will get the same result. And moreover, and this is the really important thing for us, the common value you get either by computing the iterated integral, it doesn't matter which direction you integrate, is equal to the value of the double integral. So this means that for continuous functions, double integrals can be computed very easily, because you just have to write down the corresponding iterated integral and solve it, and that's it. The situation is getting more complicated if the function is not continuous anymore, as we see here. So this is Fubini's theorem. Assume that f is continuous on this interval, then the double integral is equal to the iterated integral and this of course makes necessary that if those two are different, okay, they cannot be equal to the it is certainly not possible to compute the double integral by just looking at the iterated integrals, because you do not know which one to choose. But if those two are equal, then there might be a chance that the double integral is equal to them. Okay, and for continuous functions, this is the case. So if you have a continuous function, you are very lucky, because the situation is getting very easy, in the sense that, okay, we do not need anything in addition, okay, to what we have learned last semester for computing double integrals. You do not have to go down to the complicated limit and evaluate it. Instead of it, you can just compute this limit, the double integral here, as two integrals, first the inner and then the outer integral. And this you can do in the same way as last semester. So this Fubini's theorem tells you, okay, we can reduce the problem of computing the double integral to the results we have already obtained last semester, to the problem of computing an integral of a function of one variable. Now, you find in our textbook, actually, Fubini's theorem holds under much more general assumptions. Okay, so it is not necessary that f is continuous. F must be bounded. This is the important. F must be bounded. Then f is, but also bounded is not enough. f must be bounded, then f can be discontinuous, but just on a finite number of curves inside R, and one of those integrals must exist. Then the other one also exists, is the same, and is equal to the double integral. So this is the general formulation of Fubini's theorem. We are not going to prove it. If you are interested in the proof, you can go to higher calculus. It's not so complicated, but and actually there is kind of value. If you're just interested in doing computations, okay, of course you do not need a proof. You just apply the result. But if there is a value in seeing proofs of such results, in particular, if you want to understand some theory in much more detail or much deeper, it's certainly advisable to study proofs of such results. Okay, but at least the motivation for this result should, or the reason why this result holds, should not come as a surprise. Okay, because of the following. You see, how did we define the double integral? So we had given a function Now, I first defined this function here. So I integrated from c to d f of x, y, dy. And then I computed the integral from a to b of a of x dx. Now, you should see that this should give you the volume, right? Because of the method we have seen last semester, the method of cross sections. So you see, you have here this function, okay, the surface, which is somehow, I cannot really draw it. Maybe I try. Okay, so this is the rectangle R here, and this is the surface which is sitting above the rectangle. Now, so what is the meaning here of this one? So what you do is we fix the y direction. Okay, so we fix the y direction. So this is here is x, this is y. So we fix here the y direction, okay, because the y is fixed. Now, if we slice, okay, so you have here this solid, okay. If you slice the solid with a plane which is parallel to the xz plane with a fixed y coordinate, okay, then what you get is what we call cross sections. And this what you compute here is exactly because you go from sorry, the x is from a to b. No, sorry, I said it wrong. The x is fixed, okay, so we fix the x, we fix a plane which is like this. We slice by a plane which is like this here. So a plane which is parallel to the yz plane at some point here. Okay, so we slice it here, and what we get is an area, and this is the area of the cross section. Okay, and then we add up all those areas over from x from a to b. So this is the method of cross sections we have learned last semester. Okay, computing like this a volume of a solid we learned already last semester, and we call this the method of cross sections. Okay, and of course, if you do this, because here I do it first first I slice with a plane which is parallel to the yz plane. I get cross sections, and I add up the areas of the cross sections. If I do the same by slicing with a plane which is parallel to the xz plane, and then I sum up over those cross sections, I should get the same. Okay, but the interpretation of those two different directions, just this and this here. Okay, so this should give you the volume. Okay, and this is another way to define the volume. But you see, this is kind of subtle. Okay, because for the function which I showed you, x minus y over x plus y to the cube, this kind of heuristic here, because this is not a proof. This kind of heuristic breaks down, doesn't work. Okay, because we get something different if we compute. If you look at the solid under this function, of the solid under this function and above the xy axis, and you do these computations, then you get something different if you look at it from different directions. So this just works for, this doesn't work for all of the functions, but it's true if f is continuous. Okay, so this is Fubini's theorem. It should be clear what the power of Fubini's theorem is. It makes the task of computing a double integral easy. Okay, so let's look at some examples. Let's look at the example which I just showed you before, where we have done some numerical computations. Okay, so now we can compute this very easily. We can choose whether we want to integrate first over x or over y. So let's go first over. Actually, first should be inside. Okay, so let's go first over y, and then over x. Okay, so we have some rules. So you can write this as the integral from 0 to 2, the integral from 1 to 2, and so you can take this into two parts. Here you have x, here dy dx minus, and then you have 3, and then you have the integral from 0 to 2, the integral from 0 to 1, y squared dy dx. Now this is of course easy to compute, so you have the integral from 0 to 2 x, this is just 1 here, dx minus 3 times, and then you have the integral from 0 to 2, and this gives you, okay, so this gives you 1 over 3, so you can erase this, x. So what we get is, because this is x squared half, evaluated at 0 and 2, minus 2. Where is the mistake? It should be, didn't we see, this is not the same result. This is not the same example. Oh yeah. Wait, there is somewhere is a very stupid mistake. Who can spot it? Ah, here. Okay. Okay, so then it's slightly more complicated. So here you have dx, but you see it's not essential. So here you have 2 minus 3. Now this is 8 over 3 minus 1 over 3. So what you have is 7 over 3. So you have 2 minus, okay, now it's 14. So minus 12. Okay, this is now correct. Good. Minus 12 is also what we saw doing numerical computations. Okay, so this is this easy example. Now, another example which shows you that sometimes, because actually you have here freedom of choosing the order of integration, and sometimes this freedom will help you to compute the integral much quicker. Okay, so here, if you have this integral here, x, y, e to the x square y, where r is equal to 0, 1 times 0, 2. Okay, so of course those examples are not very complicated because we always work on a rectangle. So we just have to integrate, for instance, first from 0 to 1, first from 0 to 1, and then the outer integral from 0 to 1, the inner integral from 0 to 2. But you see, if you look at the integrand, if you first integrate with respect to y, okay, this is slightly more complicated because you have to use the integration by part. It's slightly more easy if you first integrate with respect to x, because you see that if you integrate with respect to x, then this here is the derivative here of the exponent. So you will first take the integral with respect to, so the inner integral will be with respect to x, the outer integral with respect to y. So you go y from 0 to 2, then x from 0 to 1. Now, because y is now a constant, so you can take it out. So you have x e to the x square y dx dy. This will make things slightly more easy. Okay, so what you have is, okay, so this is the integral from 0 to 2. Then you have y, and here actually you do a substitution, but you can. So the inner derivative is 2y, and then 0 to 1 dy. Okay, so what you have is 1/2, and then the integral from 0 to 2. So this is here with respect to x. So we have e to the y minus 1 dy. Okay, and this is now easy to compute. So you have okay, e to the y minus y 0 to 2. Okay, so e to the 2 minus 1, and this gives you minus, okay, so minus 3. You see that, of course, it wouldn't be more complicated if you do it in the other direction. But you can save some work, because if you, once more, if you first compute, if the inner integral, so the first one is always the inner integral, the second one is the outer integral. If the first one is with respect to y, okay, then you have to do first integration by part, which will make the computation slightly more, not complicated, but slightly longer, and you don't have to do this extra effort. Now, one special case which is good to notice is the following, where f of xy is equal to g of x times h of y. So you have a function, okay, where you can separate the part which is in x and the part which is in y. Now, if you have something like this, then if you look at the iterated integral g of x h of y, and then you have dy dx, it's good to notice that okay, so because the inner for the inner integral, okay, x is a constant, so you can take it out. So you have here g of x, and then you have the integral from c to d h of y dy dx. And now you see that the whole thing here is a constant, so you can take it out. Okay, so what you get is this is the integral of ab g of x dx times the integral of ab f of or h of y dy. You see, a double integral over such a function is getting in particular easy because you just compute it as a product of two single integrals. Okay, so we saw actually already for this function which you just saw here. For this function, it doesn't work, okay, because you cannot separate x and y. But for this function, the function which I showed you at the beginning, so the integral from 0 to 1, integral from 0 to 1, and then x square y to the cube dx dy. So actually, you can immediately write this as a product of 2. Okay, which gives you 1 over 3 times 1 over 4, which is 1 over 12. Okay. Now, up to now we have just defined the double integral for a function over a rectangle. Now we want to extend this definition to to the double integral of a function over a general domain. So now we have a general domain. So maybe I erase this. So assume we have a function f is continuous on some domain where D is bounded. What we want to do is we want to extend our definition of the double integral to double integral over such a general domain. Now the idea is very simple. So we have here this domain which is bounded. Because D is bounded, you can enclose it in a box, and not in a box, in a rectangle. Now what we do is we define a new function which we call capital F of xy, which is defined as, okay, if xi, if xy is in our domain D, then it's just the original function. If xy not in D, then 0. So 0 on the box here. Inside we just keep the original function. And now our function f is defined on a rectangle R. So we can define now the double integral over D of the original function as, okay, we just take the double integral over R of this new function here. And this is already defined. Okay, so we define this here. So we can use this here in order to define this one. So this is a very simple idea. So we have, if we have a bounded domain, okay, we find a, if D is bounded, we can certainly find a rectangle large enough which where D is inside, and we define this new function and then define this here. And the definition, first of all, makes sense because the definition will not depend on how I choose R, okay, because outside of D, anyway, 0. Okay, so the definition will not depend on how I choose R. Okay, for the definition of for a function on a rectangle, if you choose a larger one, okay, you do not get something new here. That's the first thing. The second thing is where you have actually to take a little bit more care is, I mean, this function is continuous. F is continuous on D, okay? But for this, you will need that capital F is continuous on R. Okay, that's because we said if this is a continuous function, everything is fine and this symbol will exist. Okay, but you see that using such a definition, in most of the cases, capital F will not be continuous. Okay, you just have to think about if F is sitting above D. Okay, and at the boundary of D, so what you see here, this is the boundary of D. At the boundary of D, the function will, in most of the cases, this function will not be continuous. Okay, will be continuous here outside, will be continuous inside, but not at the boundary. But this doesn't matter, okay, unless the boundary too ugly. Okay, if the boundary is too ugly, okay, it could cause problems. Okay, but as for the existence of the double integral, we do not worry about such details. I just tell you, in most of the cases, if D is not too ugly, okay, whatever this is supposed to mean, okay, in mathematical terms, it's not very precise. Okay, if the boundary of D is not too ugly, okay, this will make sense here, and you can use this definition. This you see this also in our textbook. So and this gives you now a more general definition of the double integral. Now, what every textbook is now traditionally discussing are so-called plane regions of type 1 and type 2. This is actually an easy concept. okay, so plane region of type 1. Now, this is just a special choice for D. So what is so special? You have x between a and b, and then you have two functions. Call it f1 of x and f2 of x. So this is the function f1 of x, and this is the function f2 of x. So our D is now the set of all xy such that x is between a and b, and y is between, okay, so sandwich between f2 of x and f1 of x, f2 of x and f1 of x, and f1 and f2 must be continuous on AB. So this is a so-called plane region of type 1. Okay. Now, if you have such a plane region, okay, if we have given a function, let's say f of xy continuous on D, and we want to look at the double integral. Okay, so what we have to do, according to our definition, we have to enclose the region which is bounded into a box. Okay, so we have here several choices. For instance, choose this here and this here. So this is our box here. Not our box, our rectangle. And then we define a new function capital of f, which coincides with the function inside the domain, and is 0 here outside. Okay, so what we have is, okay, we have, let's write this one down. So we have this function which is f of xy if xy is in R, 0 if xy is not in R. Okay, and using this here, we can we have defined actually this symbol here as the double integral over R now of this new function. Now, here we can use Fubini. This also needs some explanation. You see, maybe I should first, because I just mentioned that this will always exist here if the boundary of D is not too ugly. Okay, so you see here the boundary of D is given by this here. So you see, even that there are some kind of like here cusps doesn't matter, okay, because there are not so many. Okay, so this boundary would not is the reason why this works is because f1 and f2 are continuous. That's why this boundary here is not ugly. Okay, because it's not ugly, this will exist here. Now, what we want to use here is Fubini, and we can use Fubini. Now, also this needs some explanation because the function f will not be continuous. Okay, but you see, if you that's why in our textbook there is another formulation of Fubini which tells you that f must be bounded. Okay, and then continuous except of with the exception that you have a finite number of curves on which f is not continuous. Okay, so here you have this curve here. Okay, and what else? One of the iterated integrals must exist. This will be the case. Okay, so here that you can use Fubini, it needs some explanation. Okay, and if you wonder, if you look at the formulation of Fubini in our textbook, why there is additional, why there are more weaker conditions? The reason why the author gives two formulations is because the second formulation he needs for this situation here, more or less. The second formulation is not very precise, okay, because how does the author write the second formulation of Fubini? I don't remember. Smooth curves, okay. Okay, smooth curves we have defined, okay, previously. So smooth curves are those curves which I consider as nice, okay, as friendly, not too ugly. Okay, so you see, if but we can use Fubini here. So actually, it's not so complicated, and maybe I talk too much around it. So if we use Fubini, then what we have to do is, okay, we integrate from a to b, and then we integrate from c to d, and then we have this function here. But you see that, sorry, I have to write here dy dx. But you see that here you can restrict, actually, because this function is 0, okay, if you're outside of R. So when the x is fixed, okay, then we are inside of d if y satisfies this, and outside of d if y, this should be d here, and outside of d if y does not satisfy this here. So we can restrict this here to f2 of x, f1 of x, and then we have here f of x, y, dy, dx. So that's the way how we can compute the double integral of a function over a plane region of type 1. Okay, and you can think about okay, what you do is, if you look at this here, what you do is, okay, you fix an x, you fix an x, and then what you do is you compute this length. So you integrate, because you integrate from f2 of x to f1 of x. So you kind of compute here the length of this line, and then you add over x. Okay, and that's the way, that's the interpretation you can always use in order to set up the integral. Okay, so if you have given a function and you have to compute the double integral over some area, you first plot the area, and then you use this interpretation here. Okay, so for here you see why this works, because for plane region of type 1, this works here by using Fubini's theorem, and there are also plane regions of type 2 which are just the same, but x and y interchanged. Okay, then you have here everywhere you interchange x and y, but actually it's just the same. Okay, so you see in our textbook there is also a definition of plane regions of type 2, and the only thing which is different is that x and y are interchanged. Okay, so I think it's not necessary to go here into details because it's just the same. Only x and y are interchanged. Now maybe let's look at some examples. Here for double integrals, setting up the integral using this here will not be too complicated, but I know from experience students normally find it more complicated to set up than what we define later on, a triple integral. So it's good to look first at some examples for a double integral. Let's look at this example. This one, the integral, the double integral over d, 2x minus y, dA, where what is d? D is the unit circle. The unit disk. Sorry. Okay. So the first thing in solving such a exercise is always plotted. Okay. So plot the domain. This is the first thing. Now, okay. So we this obviously is a plane region of type 1. So we can use the result which we have just seen here. But to say it more easily, okay, so you first choose a direction. Okay, you can also interpret this as a plane region of type 2, okay, because you could look at it like this. But let's look at it as a plane region of type 1. So the outer integral, okay, is over x, okay, and the inner integral is over y. Okay. Now this is kind of awkward because I just said that the inner integral is first and the outer is second. Now we change it. Okay, so the outer is first and the inner is second. Okay, but if the computation is different. So we first go over x, then we go over y. So you have our x is from -1 to 1. So which means you fix some x value here, x0, which is between -1 and 1. And now with y, you go from minus the root 1 minus x squared. And here you have the root 1 minus x squared. And then you have 2x minus y dA. The dA, becomes, because we use Fubini, so the dA becomes dy dx. Okay, so now this is not too complicated. So we break it into two parts. So we have here 2. And we have here the integral from minus square root 1 minus x squared, square root 1 minus x squared. And here we have x minus, and here we have the integral from -1 to 1. And then we have here y dy. Okay, so okay, so you have here 2 times the integral from -1 to 1. But this actually I should write here dx, dy dx, and here I have also dy dx. Okay, so here because the inner integration is with respect to x, so we can take out the x, and what we get here is 4 times and then the square root 1 minus x squared dx. And what we have here is minus. So actually, you see here, because the inner integral will get 0. Okay, so this means that the whole thing is 0. So you can forget about this. And here you see that because this function here is odd. Okay, so this will be equal to 0. It's the same reason here, because this function here is odd. So this will be equal to 0. So this will also be equal to 0. I don't have to compute this. So everything is 0. So this is one example, a very, very easy one. Now one more. The function f of xy on the plane region on D bounded by y is equal to x minus 1. Y squared is equal to 2x plus 6. Okay. So we have here a parabola. This is y. So now, if okay, y is okay. So you have here this parabola. This here is -3, and you have this line here. So 0 -1. Okay, then roughly. Okay, so you have this here, and our origin is this here. Now. Here it is better to interpret this region as a plane region of type 2. So of course it's better to look at it like this here, because then you have then you don't have to break the integral, your consideration into 2 parts. Okay, so if you would look at it as a plane region of a plane region of type 1, then you have to break it in here into 2 parts. But if it is a plane region of type 2, you just have to consider 1 part. So this makes it seems to make it slightly easier. What we first have to compute is this point of intersection here. So we have x minus 1 square is equal to 2x plus 6. So x square minus 4x plus 1 minus 5 is equal to 0. So what is this? X minus, I have to solve it. Okay. 16 minus 20 over 2. Okay, so 6, 4, 10, 5, and 6 minus 1. Okay, so this here is minus 1. And this here is 5. And the corresponding y values you see here. So we have to go from. So this is just equal to equals. So we will go like this here. Okay. So the double integral over d of x y dA is equal to. Now, first, so if x is equal to minus 1, y will be equal to minus 2. So from minus 2 to, if x is equal to 5, y will be equal to 4. And then, so this is, now we fix here some of those directions. So for instance, this one. And now we have to integrate from the parabola up to the line. So we are first with respect to y, so we have to solve this here for x. So we have here from y square minus 6 half going up to y plus 1, and then x y d. Now y dx, sorry, dx dy. Okay, and if you solve this, then you get 36. You see, this seems to be slightly more easier, okay, than going the other direction. So than looking at this plane region as a region of type 1. Maybe let's also write down what do we get if we look at it as a plane region of type 1. So then this integral would become the integral that from so first in x direction now you go from minus 3 to minus 1. Then this integral here. So now the integral with respect to y. So what you do is from minus square root of 2x plus 6 to the square root of 2x plus 6, and then you have x times y times dy dx plus, and then you have the integral from now from minus 1 to 5. But now the upper boundary becomes x minus 1, so you go from x minus 1 up to the square root of 2x plus 6, and then you have x, y, dy, dx. The author of our textbook, because you see this example is in our textbook, the author writes down both expressions, and then writes this is more complicated to compute than this one. It's not true, because you see that here, if you look at the inner integral, okay, you can take out the x. This is an odd function, so it will be 0. So you can forget about this. Okay, so this one is equal to 0. So I would claim they are both, the complexity of computing this is the same. It's not really that, as the author claims, it's not really that this is more complicated than this one. So, but this is due to the function here. So sometimes this can really help, and we will see that the order of integration sometimes is very essential. So for some examples, we will see that if we change the order of integration, we will see this on Thursday. Then we will be able to compute the double integral. If we do not change the order of integration, we will not be able to compute the double integral. So the order of integration will be very essential. And in some cases, not for this example, this is not a good example, but for some examples, the double integral becomes easier if you so of course theoretically you get the same value if you no matter whether you first go over x and then over y or the other way around. But in terms of computation or complexity, sometimes it's more easy to do it in either of the one directions, and it pays off to think sometimes, in particular then for the Heu where you are under where you have a time pressure. Sometimes it pays off to first to think which direction you choose, then to set up the integral, and then to solve it. Okay, we will see more examples next time. So, any questions? If not, then we will make a break of 10 minutes, and then we will go on.